All right. So me and Richard worked on a divide and conquer algorithm for the eigen problem. This particular algorithm is somewhat in its infancy, and it's more or less the only game in town with some kind of exceptions of special cases like Yaloo algorithm. But anyways, the basic idea here is you have a matrix with a spectrum, and you want to somehow split the spectrum to divide the problem and decouple it. The basic intuition is that, say, if you have, from linear algebra, if you have two different eigenvalues, you know that their eigenspaces are going to be orthogonal just by this kind of simple argument. So basically, the problem will naturally just decouple into these invariant subspaces. And this holds in general, even without, basically in the non-symmetric case, we can get a hold of an invariant subspace that maps into itself, and you can use that to decouple the problem completely. And the basic idea is that, I've drawn two lines here. One line is kind of how our algorithm works, and it'll split based on lines. And then the other one is a circle. And the circle, you can use a Mobius transform to map to any kind of generalized circle or line or whatnot as you want. But you want to construct these projectors. So you want to be able to split the thing and then take all the kind of eigenspaces with regards to these eigenvectors and separate the problem out that way. And the basic argument is that if you have a matrix AK, this will basically split the eigenvalues in terms of eigenvalues of modulus greater than 1 and modulus less than 1. And yeah, if you act on this matrix with an eigenvector corresponding to an eigenvalue greater than 1, it's going to map it to the same vector, and if it's less than 1, it'll map it to 0. And if you use this projector to do a coordinate transform on the original matrix, you'll basically get a matrix of this form where E is basically converging hopefully to 0. And if you can get this E to be 0, then the spectrum of, or the eigenvalues of A is going to be completely determined by the eigenvalues of this guy and the eigenvalues of that guy, and the problem just completely decouples. But the main issue in some sense is being able to choose a line such that this iteration converges quickly. And the main downfall of it is that, okay, well, if I'm given a matrix, I don't know what the spectrum is at all, so I just have to choose a line and hope to God that it's good, which is not a game I like playing. But so like the worst case is you choose a line that's really bad, it doesn't converge, and you've done all this work for absolutely nothing. And so you kind of have to get creative, because a lot of the parallelism that the algorithm relies on is already built into LAPACK, so there's not much. But somehow there's this idea that the problem matrices are ones with bad pseudospectra, and there's this idea from random matrix theory, mainly Dyson-Brownian motion, that in some sense if you add noise to your matrix, without even knowing what the eigenvalues are, the eigenvalues will want to separate up to a Brownian motion, so it'll be easier for you to make line splits. So this is just a kind of example to kind of showing this. If we start with a Jordan block, let's say, I think it's 500 eigenvalues just at this block, and you add a machine precision perturbation of this, so 10 to the minus 16. I think we had like 10 to the minus 10 or something like this in this case, but it like literally the eigenvalues will more or less deterministically go in a circle of about radius 1. So the randomness somehow is more or less eaten away, but there's a stochastic differential equation that expresses how the eigenvalues will evolve, and it's basically up to this Brownian motion they'll want to separate from each other. And so there's this kind of trade-off of corrupting your matrix and corrupting your spectra, and getting your algorithm to actually make successful splits and move on. And we basically experiment with this with some success, so if you're interested, come check us out.